Good morning, students. Okay. So yesterday we started a topic called induced electric field. Okay. So introduction part of this induced electric field we have seen yesterday. So a quick revision. Okay. So what we did? So we considered a constant magnetic field. Okay. So we considered a constant magnetic field and a question I raised. Okay. So what is that question? So if I consider magnetic field, so if I place a coil inside, so what will happen? What will happen? Nothing will happen. Why? Because magnetic field is constant. If I place a coil, no induced current will be there, right? So if I increase the magnetic field, so it will start from a time t equals to 0, magnetic field equals to 0. Slowly what will happen? Magnetic field increases. All these questions we discussed yesterday. Okay. So if time t equals 0, magnetic field equals to 0. So slowly what will happen? Magnetic field increases. If magnetic field increases, opposition outside, so anti-clockwise current will be developed in the coil. Right. So anti-clockwise current, induced current developed in the coil. So what is the question raised? So if magnetic field is there, so if a charged particle, if I place in the magnetic field, then what will happen? So magnetic field never gives the kinetic energy to the charged particles. Just it will rotate, right? So V bar cross B bar, it will changes the direction. But whatever the speed it will be, speed it won't change. It in the sense magnetic field. But if it is electric field, acceleration will be there. We know that is EQ by M, right? Now, if magnetic field increases, induced current developed. If induced current developed in the sense charged particles are moving. Charged particles are moving in the sense due to magnetic field or due to change in the magnetic field. Change in the magnetic field. So, charged particles initially at rest. If V equals 0, charged particles initially at rest. Now, if magnetic field changes, then slowly they started moving. So, due to what it started moving? Magnetic field, it won't give any kinetic energy. So, charged particles won't move. Now, the charged particles are moving in the sense due to what? Due to electric field. Due to electric field. Electric field is there inside, right? So, if electric field is there in the sense, who gave that electric field? Change in the magnetic field. Now, what is the story? So, change in the magnetic field, change in the magnetic field develops electric field, and that electric field we call it as induced electric field. Okay. So, change in the magnetic field develops a new type of electric field. Up to now we didn't study about that. So, electric field we know, but whatever we are studying now, that electric field is not that old electric field. That is a new electric field that we call it as induced electric field. Now, basic things we know. What is that? Electric field and magnetic field practically separately they won't be there. If electric field is there, magnetic field will be there. If magnetic field will be there, in the sense at that instant electric field also will be there. Separately we won't get practically. If electric field will be there, magnetic field will be there. So if magnetic field is there at a place, in the sense we can tell electric field is also there. So what is that electric field? That will be induced electric field. Right? Clear about the point? Now we have to discuss about this induced electric field. And what is the direction? What is the magnitude? Right? So everything we have to discuss. Clear about that point? What is the basic point? Induced electric field, from where we will get? From change in the magnetic field. If change is not there, then nothing will be there. Charged particles won't move. In the sense, induced electric field is not there. If magnetic field changes, then charged particle starts moving. If charged particle starts moving, due to magnetic field it won't move. Then due to what it is moving? Due to induced electric field. Clear about this point, right? Next point. Okay, sir. You said induced electric field will be there. Now, what is the direction of that induced electric field and what is the magnitude of induced electric field? Again, 2 points. Right? So, what are the two doubts arised? What is the direction of the induced electric field and what is the magnitude of that? And what is the magnitude of that? If I compare with old electric field and now the present induced electric field, what is the differences? 1 or 2 differences, we will see. Right? So, now we will concentrate on the direction. For example, if I consider the change in the magnetic field, whether it is increase in magnetic field or decrease in magnetic field. Assume increase in magnetic field and inward magnetic field is there. Okay. Now what I am doing, I considered a charged particle positive charge, positron, right? So assume it is the center, and at a certain distance I consider a charged particle. At a distance R, assume, okay? Now what will happen? What will happen? This charged particle will move or what? Definitely it will move. Why? Because change in magnetic field. If change in magnetic field is there, then induced electric field will be developed. We already studied. So if we already studied, then this charged particle definitely it will move. But now in which direction it will move we want. For that, what we have to do? First you have to draw an imaginary loop. First step, what is that? We have to draw the imaginary loop. So draw an imaginary loop here. Okay. So it is a loop of just imaginary. It's just an imaginary. Now, in which direction it will move? If we draw an imaginary loop, then we know the concept. What is that? Opposition according to Lenz's law. So we can apply the same Lenz's law. So tell me, what is the Lenz's law? Inward magnetic field is increasing. So opposition in which direction? Opposition will be outward. Clear about that point? Opposition will be outward. So if opposition is outward, anti-clockwise, right? So what is induced current direction? Anti-clockwise direction. If it is anti-clockwise direction, now you can tell what is the direction of this induced electric field. So can I draw a tangent here? Already we studied in properties of electric field lines. Whenever the charged particle, whenever a particle, if a charged particle is there, if a field line, so positive to negative charge, electric field lines. These are the electric field lines always from positive to negative. So at any point if I draw the tangent, what it will use? It will use electric field direction at that point. Now here, charged particle is moving. In the sense, in this direction I can tell force will be there. Getting the point? In this direction what will be there? Force will be there. That force is nothing but, what type of force? Electric force. If electric force is in this direction, then automatically force and field will be in the same direction we know. Getting the point? Force and field always will be in the same direction we know. So this is the force due to what? Due to the induced electric field. So I can draw a tangent here. Force, right? Tangent. Tangent. What are all these tangents? All these tangents I can tell that is the force. If the force direction is in this direction due to the induced electric field, then induced electric field direction will be the same direction of the force again. So I can tell this circular loop here. I can tell this is electric field line for this charge. So little new thing for you. Try to understand the point again, or else try to listen again. Okay. So if I consider a charged particle, if change in magnetic field is there, then what will happen? This charged particle definitely it will move. It is moving due to what? Due to change in the magnetic field. Change in magnetic field produces the induced electric field. Due to that induced electric field, the charged particle is moving. In which direction it is moving? You have to draw an imaginary loop. With that imaginary loop, what we have to do? You have to see in which direction it is, the current will form. Due to Lenz's law, by applying this Lenz's law, we know the direction of the induced current. If you know the direction of the induced current, in that direction charged particle, positive charged particle will move. We know that. If charged particle is moving, it is moving. In the sense what? Some force will be there. Right? So if force in which direction? You have to draw the tangents. You have to draw the tangents. That tangent will give you the direction of the force. Now we know force direction and field direction will be same. Now finally what I can conclude, this is the direction of the electric field line. Here what I can conclude, electric field lines forms a closed loop. Try to understand? So this is the electric field line for this positive charge. Now what I can tell, electric field lines, here induced electric field lines, I am talking about induced electric field lines will form a closed loop. Closed loop. But there normal electric field we studied in the first chapter. There just electric field we studied. If only electric field is there, in the sense what? It won't form a closed loop we studied. It won't form a closed loop. If it won't form a closed loop there, we call it as a conservative force. So here closed loop formed. So if closed loop formed, in the sense what? It is non-conservative. Why it is non-conservative? For one circular loop, there work done will be 0. But here work done for one complete loop will be work done formula. Force into displacement. So what is force? EQ, electric field into charge. What is the distance travelled? It is 2 pi r. So if radius is r, that will be 2 pi r. So force into 2 pi r. So work done is not equals to 0. If work done is not equals to 0, we can call it as non-conservative force. Why it is non-conservative force? Here electric field lines will form a closed loop. Try to understand all the points. Why it forms a closed loop? Understood the point? Force and field will be in the same direction. If you join all the points, then force and field directions will be same. Then it will form a closed loop. Now these dotted lines I can conclude it as electric field lines. This dotted circular loop we call as what? We call as electric field lines which forms a closed loop. So we call it as non-conservative. So why non-conservative? Displacement. You can ask, sir, displacement, no, it will be 0. No, but here it won't be 0, it will be 2 pi r. So EQ into 2 pi r, which is non-conservative, it forms a closed loop. Points, what you have to remember. Clear? Next point. Next point. Okay? One more example I will give, then you can understand it easily. Right. Okay? Pause the video and try to do this question. For example, outward magnetic field I gave. So what is the magnetic field here? Outward. So magnetic field increasing, and from assume this is center. From the center I placed a positive charge again, initially at rest. At a distance r. This is an imaginary center. Okay. So with respect to r distance, we place a positive charge initially at rest. Now magnetic field is varying. If magnetic field varies, what will happen? Induced electric field develops. Due to that induced electric field, what will happen? This positive charge particle, definitely it will move. Now my question is, in which direction this charged particle will move? Okay. Pause the video. Try to do per minute. Okay. So I will continue my discussion. Pause the video and think. So now positive charged particle, outward magnetic field is there. Now what we have to do? We have to draw an imaginary loop first. So outward increases. Outward magnetic field is increases according to Lenz's law. Opposition inward, right? So this will be the current direction. So clockwise direction, right? So the direction of the induced current is clockwise. So in which direction this positive charged particle will move? In the clockwise direction. So force. In the force direction, what will be there? Field direction also will be there or not? Field also you have to draw a tangent. So this is field direction I can tell. So electric field line for this positive charge in this example is clockwise direction. Again it formed a closed loop. So induced electric field always forms a closed loop. It is non-conservative force. Please try to understand. Right? Next, one more thing. So now try to extend the discussion. Right? Concentrate. Now this dotted lines will use you what? It is a loop or it is the induced electric field direction. It is induced electric field direction. So I can tell this loop is called as induced electric field line. Induced electric field line. Okay? Induced electric field line. Okay? So induced electric field lines. This is not a loop. This is induced electric field line. One more thing. So if I consider this is the field line, according to the old concept in the first chapter, what we studied is at any point on the field line, at any point, if I consider point A, right? So if I consider point B, right? So at any points, if I consider 2 points here, if I consider old electric field, we call it as equipotential surface, if you remember. What concept is that? Please try to revise the first chapter. We call it as equipotential surface. Potential at any point will be constant. Potential at any point will be constant. Now what we can write? Old electric field I am telling, not the induced electric field. Old electric field. What is the formula? Line integral of E bar dot dl bar, which is equals to 0. Why E bar dot dl bar equals to 0? What it will give? Integral E bar dot dl bar will gives you potential difference. Integral E bar dot dl bar. Please try to revise the previous chapters. Line integral of E bar dot dl bar will gives you potential difference. Now potential at all the points on this surface is same according to the world electric field. So potential is the same. In the sense potential difference will be 0 according to the world electric field. Now according to this induced electric field. According to this induced electric field. Think for a minute. According to this induced electric field, what I can write this one? Can I write line integral of E bar dot dl bar equals to 0? I don't think so. Think about that. In the world electric field, we call it as equipotential surface and potential difference will be 0. So line integral of E bar dot dl bar we can write it as 0. Now here can I write 0? No. Why? Current direction is there. If current direction is there, EMF is developed. So what is the point you have to remember here is, try to draw the equivalent diagram for this. Already we discussed in the last classes. Alright. So draw the equivalent diagram. Current direction is there or not? Yes, clockwise direction, current is there. Assume. If you draw an imaginary loop, current will be there. If current is there in the sense, induced EMF is there or not? Getting the point? If current is there, if I draw an imaginary loop, current is there. If current is there in the sense, induced EMF will be there. Current is there in the sense what? This charged particle is moving. If the charged particle is moving, what will happen? Current will be generated. We know I equals to Q by T. Right? Now charged particle is moving. So current will be generated. If current is there in the sense what? Induced EMF will be there. Induced EMF will be there due to what? Due to the line integral of E bar dot dl bar that induced EMF developed here. So what I can write here, according to the induced electric field, I can write line integral of E bar dot dl bar, which is equals to what? Induced EMF. So can I write it as EMF? This is the formula, very important here. If you understand this, then whatever the things it may be, we can do it easily. So what is that? Line integral of E bar dot dl bar equals to what? Induced EMF. Induced EMF. Now formulas, right? Can I rub this? Right. Now formulas, line integral of E bar dot dl bar, I can write as what? I can write as EMF. Induced EMF. Now induced EMF formula we know. According to Faraday's laws, I can write as minus d phi by dt. So this is the formula for induced electric field. Right? Line integral of E bar dot dl bar equals to 0. There in the world electric field. Now according to the induced electric field, line integral of E bar dot dl bar, which is equals to minus d phi by dt. Minus indicates opposition again. Right? Opposition already we considered. So directly according to the magnitude if you are writing, you can eliminate that minus. Clear? Now take the same example and try to calculate. Alright? I'll take an example. So this is the final relation, what you have to remember in this concept. So comparison also I did. Try to write the notes, will be easy for you. So what is the first point? Induced electric field will be developed due to the change in the magnetic field. First point. Right? So second point, what is that? It is non-conservative. Why it is non-conservative? Induced electric field forms a closed loop. Alright? Next, in the world electric field, line integral of E bar dot dl bar equals to 0. But here, it gives you the induced EMF. It gives you induced EMF in the sense, the formula is minus d phi by dt. Clear? These are the properties what I said last 4 or 5. Right. Now start. Okay? Take a question. For example, consider inward magnetic field and assume that magnetic field is varying with respect to time. B equals to B of t. Okay? Magnetic field is varying with respect to time. Varying with respect to time. Right. Now I consider a positive charged particle here. Okay, at a distance r, imaginary center. From the imaginary center I placed at a distance r a positive charge, a positron. So what will happen? We know it is increasing magnetic field. It is increasing in the magnetic field. So opposition in this direction, right? So definitely the charged particle will go in this direction. Right? Now, what to calculate? Try to apply this formula. Try to apply this formula and find the induced electric field. My question is, can I write here? Yes. Find the induced electric field. Yes, if you understand this, whatever the question you can do, we'll go for the next concept. Okay. Find the induced electric field in this case. Done. What you have to do? Take the formula minus. No need to consider that minus. Why? Because already opposition we know. With respect to that opposition only, this direction I considered, right? So this is the electric field line, which forms a closed loop. Now what I can write? Line integral of E bar dot dl bar. Dot dl bar in the sense cos theta. So integral E bar or EDL cos theta can I write? EDL cos theta, which is equals to d phi by dt. Now electric field constant throughout, and what is the angle between E and dl? E in this direction, dl also in the same direction, so cos 0 1. Dl in the sense you have to consider a small element here. That element direction and as well as electric field direction will be same. So cos 0 1. So theta value is 0. Right? So cos 0 1. Next EDL, electric field constant throughout, integral dl, which is equals to d by dt of flux. You have to calculate that flux, right? So what is flux formula? Can I write dA cos theta again? So area and magnetic field. Now theta indicates angle between area and magnetic field. Magnetic field in which direction? Inward. For this loop, area vector also I can consider inward. So theta 0 again, cos 0 1. Again here also theta value is 0. Here electric field and dl. Here magnetic field and area. Theta value is 0. Next, flux we have to calculate. So what is B? B is nothing but B of t. It is varying. So B of t. What is area? Center is R. From the center, positron is at a distance R. So area, can I write it as pi r square? So pi r square. So flux phi, which is equals to B of t pi r square. So this is the flux. Right? That flux we can substitute here. So E constant, integral dl, which is equals to d by dt of this flux. What is that? B of t pi r square. B of t pi r square. Now what is this integral dl? Integral dl in the sense this element we considered, that element on complete circular path it is there or not. So I can write as 0 to 2 pi r. So E into 2 pi r, which is equals to now B of t into pi r square. So it is varying with respect to time, right? And pi r square. Now pi r square constant you can throw out. Pi r square, throw out of the differentiation. Now what you have to do? D by dt of B of t. Right? Clear about the point? Now 1 r cancelled and pi cancelled. So finally induced electric field, which is equals to 1 r is there. So r by 2, it is d B by dt. B of t you can write, no problems. Directly we can write as B, where B equals to B of t. Right? Where B which is equals to B of t. So we have to differentiate the magnetic field which is changing and into R by 2. We call it as induced electric field. Right? So induced electric field equals to R by 2 into dB by dt. So this is the complete concept of induced electric field. So now whatever the question might be, we can do or not. So for example, B I gave it as B naught t square. B naught t square, and remaining terms are same. Find induced electric field. What you have to do? E, which is equals to R by 2 d by dt of what is magnetic field? B naught into t square. You have to differentiate B naught t square. You have to differentiate B naught t square. Differentiate that, what you will get? E, which is equals to E, which is equals to R by 2 d by dt of B naught into t square. B naught constant throughout. Right? D by dt of t square 2t. So 2 gets cancelled. So what is induced electric field? E, which is equals to R B naught into t. Right? So that will be the induced electric field. So you can take any expression and you can calculate the induced electric field in that case. Why? If magnetic field varies, induced electric field varies. Clear? This is the electric field line. how to draw this electric field and clear about that. So this is the concept of induced electric field, right? Next. Next, important topic for board level, self-induction. Okay, so next topic, self-induction. Two concepts will be there here, self-induction and mutual induction. If you understand those two concepts, almost chapter is done, right? So what do you mean by this self-induction? Very important concepts, concentrate, okay? Self-induction. Try to understand this word, very important. Self, in the sense, if I consider a coil, concentrate, story, a coil which is having n turns, okay? A coil which is having n turns like this, right? Which is having n turns connected to a battery, right? So a coil which is having n turns, a conductor I consider which is having n turns like this, okay? So connected to a battery. What will happen? Slowly current increases. Try to understand the point. I will tell the difference between this we call as an inductor. We call it as an inductor, okay? So first you have to understand the concept, then I will compare what is inductor and what is capacitor and what is the differences, right? First try to understand the concept. Now, if a coil which is connected to a battery, what will happen? So current starts flowing from higher potential to lower potential, we know that, okay? So it started flowing from higher to lower. Then here what will happen? This conductor will allow the current, we know it will allow. So now try to understand, initially at time t equals to 0, I equals to 0. Try to understand all the points. At time t equals to 0, I equals to 0. Okay. Now slowly the current is flowing, current is increasing. If current is increasing, then what will happen? Current is increasing, change is there or not? Already we discussed in this chapter that change word is important. If current is increasing, change is there. What change is there? Current is changing. If current is changing, then what will happen? Magnetic flux links with the coil changes. If current changes, then magnetic flux links with the coil changes. If magnetic flux link with the coil changes, then what will happen? Opposition will be developed. Opposition will be developed in the same coil or in the other coil? In the same coil. Current is flowing in which coil? In the same coil. Opposition developed in which coil? In the same coil. So we call it as a self-induction. Okay? Self, in the sense in the same coil. Current changing in the same coil and opposition developed in the same coil, and due to that opposition, what happened? Induced current developed in the same coil. So that phenomenon we call it as self-induction. Clear about the concept? Now try to understand the story. At time t equals 0, I equals 0. If time increases, what will happen? Current increases. Right? So if time increases, what will happen? Current increases. So if current increases, in the sense change is there. If change is there, due to that change, what will happen? So say coil is like this, current is going in this direction. So coil is like this, current is going in this direction. Right? So current is going in this direction. Now this is the change. Change is there in the sense if current is inward, what will happen? Current is inward, what you have to do? So this will give you magnetic field direction. So current direction, this if you curl the fingers, current direction will get. Right? So if you consider a coil, right? So current increases. If current increases, magnetic field in which direction it will change? It will oppose the current which is there in the circuit, or it will support? It opposes. Already we know that. It opposes the direction of the current in the circuit. Opposes in the sense, now induced EMF will be developed in the coil in such a way that it opposes the current in the circuit. Is that clear? So opposes. Opposes in which direction? Opposite to the direction of the current in the circuit. So in this direction, induced EMF will be there, and that induced EMF we call it as self-induction. That concept, that phenomenon we call it as self-induction. And that EMF, in which direction it will be? If current increases, then opposition. We know a magnetic field increases. How the magnetic field increases? Current should increase. Yes or no? Directly magnetic field will increase. Some process should be there. What is that process here? According to this story, current is increasing. Okay? So if current is increasing, magnetic field increases. If magnetic field increases, opposition. Right? So if opposition in this direction, induced EMF also will be in the direction of the current. Right? So that will be opposing what? Opposing the direction of the current in the circuit. So this direction I can tell the induced EMF. In this direction, which opposes. This is case 1. Now case 2. For example, consider the coil connected to the battery. Okay? Connected to the battery. Now, current decreasing here. I decreasing. So, pause the video and think about what is the direction of induced EMF in the coil. What is the direction of induced EMF in the coil? In the first class of electromagnetic induction I said. Right? If magnetic field increases, opposition in the other direction. If magnetic field decreases, opposition will be in the same direction. Same here. What is that? So here current decreasing or current increasing? Current decreasing. If current decreases, then what will happen? Current decreases, then what will happen to magnetic field? Decreases. If magnetic field decreases, opposition will be in the same direction or in the other direction? In the same direction, right? Now here, tell me, induced EMF direction, in the direction of the current. This is induced EMF. In the direction of the current. Here current is increasing. So if current increasing, then induced EMF direction will be opposing the direction of the current in the circuit. So this phenomenon, we call it as self-induction. So varying the current in the same coil, flux linkage changes in the same coil, and induced current developed in the same coil. So everything in the same coil. Current which is going in the coil, flux linkages changes in the same coil, and induced EMF developed in the same coil, and induced current also developed in the same coil. This phenomenon we call it as self-induction. Clear about that point? Right? Now we will see some equations. Right? See the equations now. Now in the coil, I will draw a small circuit. You can understand. Okay? Now, assume current is changing, whether increasing or decreasing. Current changes, assume that. Changes. Might be increases, might be decreases. Don't worry about that. Okay? Now tell me the story. If current changes, flux changes, or if flux changes, current changes. First you have to write an equation in the sense, you have to know the concept, right? What is that concept? If flux changes, this current changes, or due to this current is changing in the circuit, then flux changes. First current should change in the circuit, right? Then flux changes. So flux is directly proportional to current. If current increases, flux increases. So that's why you have to write like this. Okay, you can't write I is directly proportional to phi. Phi is directly proportional. Some of you will ask, sir, both are same. No, why you are confusing us? No. If current increasing, then flux increases. You have to write like this, right? So if I is directly proportional to phi, if you write, then how you will pronounce that? Flux should increase, then current will increase. No. So first current will increase, then flux changes will be there in the coil, right? So now phi is directly proportional to I. So this phi for one coil. Here one coil is there or more turns are there? More turns are there. So if more turns are there, net flux we have to calculate. Net flux we have to calculate. So what is that net flux? N times of phi. Okay, we call it as flux linkages. We know that, right? So which is directly proportional to the current. Okay, so if you remove proportional, we will get a constant L times of I. This L is a constant, proportionality constant, or we call it as coefficient of self-inductance. L we call it as coefficient of self-inductance. I will discuss about L later after 5-10 minutes. Okay, don't worry about that. Okay, so N phi, which is equals to L times of I. So where L is the coefficient of self-inductance, it depends on the material what we consider here, right? We consider coil, we consider conductor, L depends on that. So L, according to the formula, I can write as L, which is equals to N phi by I. Okay, so if you want to calculate the coefficient of self-inductance, we can write this formula. So the basic principle, what is that? So the change in flux is directly proportional to the current in the circuit. So if current in the circuit changes, then flux changes, right? So net flux changes. So one coil I consider, so that's why I have written as phi. Why I have written as N phi? Only one coil I didn't consider here. I considered many turns. I considered many turns, n number of turns. So that's why we have to consider the net flux. So N phi is directly proportional to I. So N phi, which is equals to Li, where L, which is equals to N phi by I. So this is the formula for coefficient of self-inductance. Now what we want? We don't want this L value just on the way it came, so I have written. What we want? We want to calculate the induced EMF developed in the coil. What we want? We want the induced EMF developed in the coil. What we want? We want the induced EMF developed in the coil. Okay? Induced EMF developed in the coil. So tell me, according to Faraday's laws, we know the formula E, which is equals to minus d phi by dt. So E, which is equals to minus d by dt of flux. Right? So flux. Is it exact formula what I have written? Okay, not bad. We can consider. But phi again, for one turn or for n number of turns? For one turn. So how many turns are there? N turns I consider. So instead of writing phi, what you have to write? So you have to write it as N phi. Understood the point? Right? So phi is also correct. Now why I have changed it to n times of phi? Net flux we have to consider again. So n is constant throughout. So what I can write now? Minus n d phi by dt. Right? So constants we can throw. This is the exact formula of induced EMF. I think we discussed in Faraday's laws. Right? Now n again I am sending inside. Just I have written the formula. So minus d by dt of n times of phi. Now n phi is nothing but, according to this concept, come back to this concept. That is according to the Faraday's law we have written. Come back to self-induction and we have to calculate the induced EMF here in this concept. Right? So n phi I can write as what? Li. So instead of n phi, I can write equals to minus d by dt of Li. Right? So we know that n phi, which is equals to Li. So where L is coefficient of self-inductance. So that is a constant throughout, minus L di by dt. Right? Important formula to calculate induced EMF in the coil which is having n turns. What is the formula? E equals to minus L di by dt. Di by dt in the sense change in the current with respect to time. That change is important. So that's why we got it as di by dt, not just I. Okay, I in the sense that is constant, di by dt in the sense what? The current should change with respect to time. If that change is there, then only induced EMF will be developed in the coil. In the same coil or in the other coil? In the same coil. So that's why we call it as self-induction. Clear about the point? Right? So E equals to minus L di by dt. Right? Now we'll see some cases about how it is opposing and how to replace and all. Is that clear? Can I run? Right. Okay. Now what I am doing is case 1. Consider a coil connected to a battery and assume current is increasing in that circuit. Okay, current is increasing in the circuit. First case. Second case, assume same coil connected to a battery, right? And current is decreasing. Here current is increasing and here current is decreasing. Current is increasing and current is decreasing. Current increasing and current decreasing, right? Now, if current increases, already we said, current is increasing, opposition in which direction? So assume direction of the current. So no need to tell about the direction of the current. Why? Because battery is there. So positive terminal to negative terminal we know, right? So the current, induced EMF, current increasing, opposing or it will be in the same direction? Opposing or it will be in the same direction? Opposing, right? So now induced EMF direction will be in this direction. Now can I replace this inductor we call, try to write a point, we call it as an inductor, okay? So now induced EMF direction opposes the change in the current in the circuit. Now can I replace this inductor with a battery? Try to understand. I am replacing this inductor with a battery. With a battery. So how that battery should be? Where the positive terminal should be and where the negative terminal should be? Induced EMF in this direction. In the sense of current also, which is opposing the current which is there in the circuit. Current also should oppose. So can I replace this inductor with this battery? And what is the EMF of this battery? What is the EMF of this battery? So E, which is equals to L di by dt. So why minus I eliminated? Already we know that is opposition. Direction already we change. So that's why minus again, no need to write. So what is the EMF of this battery? It is E equals to L di by dt. Now the equivalent circuit will be like this, right? So how we can draw? So one battery instead of an inductor and the another battery, the source battery, right? So E, which is equals to L di by dt, and here if you assume EMF is E, so this will be E. So equivalent circuit, right? So how to calculate potential differences and all we will see later. Don't worry about that. So first, up to now, how we have to replace an inductor with a battery. So where positive terminal should be and where negative terminal should be. It depends on the direction of the induced EMF first. So opposition you have to see. So EMF in this direction, in the sense current also should oppose the current. Should oppose the current in the circuit. Induced current, right? So positive and negative. So what is that EMF? We know, already we derived. So L di by dt. Now current decreasing. Start doing. Pause the video. Start doing. So current direction in the circuit. Right. Now current is decreasing, already we know if current decreases, induced EMF will be in the same direction or in the opposite direction? In the same direction. If induced EMF will be in the same direction, current also will be in the same direction. So if I replace this inductor, how we can replace? Now in the same direction, right? So if it is in the same direction, now here negative terminal will be there, here positive terminal will be there. Right? So how to calculate EMF? So EMF equals to L di by dt again. Right? So what is the equivalent circuit? So if I eliminate the inductor, this is the battery. Now these two are supporting or opposing? See, supporting. Positive terminal to negative and again positive terminal to negative. Supporting situation this one, okay? Net EMF in the sense E1 plus E2. Here net EMF in the sense, if I write E1 and E2, it is E1 minus E2. Why? Because it is not supposing. It is not supporting, right? So current is coming in this direction, here current is coming in that direction. Both are opposite in the direction. This is opposing case and this is supporting case. If you want to calculate the net EMF, right? So this is E equals to L di by dt and this is the source. Okay? Try to see the concept, how to replace an inductor with a battery. We'll do a question and we'll close the session, okay? We'll do a question on this We'll try to calculate the potential difference, then we'll close the concept. Okay? So, for example, one question I will do and one I will give a task for you, then we'll close the session. Okay? So, see now, consider inductor, consider a battery, consider a resistor. Right? This is point A and point B, and current is flowing in this direction. So assume that is 2 amperes, right? And here L value is constant. We have to give that L value. So I am giving it as 2 millihenry. Henry is the unit of L. Okay? So Henry is a scientist who has developed that coefficient of self inductance. So unit is Henry, millihenry. Very small value I consider. Okay? So battery 5 volts and resistance 2 ohms, right? Current is 2 amperes. Now, one more thing I have to give in the question. If the concepts are clear, you can tell me. What is that? Here inductor is there, in the sense change should be there, or else this term will be 0. Here battery won't be there. So that change should be there. What is that change? Find, okay, first I will give the change. The change is di by dt, which is equals to 1 ampere per second, 1 ampere per second, increasing. This I will do, right? Next, di by dt 1 ampere per second, decreasing. This you have to do, right? This I will do, increasing. So now di by dt is increasing, in the sense current increasing. If current increases, how we can replace this inductor? First point. So what is the question? In the two cases, find the potential difference between A and B. Question? Find the potential difference between A and B. Clear about the point? Now this one I will do, this one you have to do. And what is the question? Find the potential difference between A and B. Now you have to replace this inductor with a battery. How? Current is increasing. If current increases, opposition in this direction. If opposition in this direction, so tell me current also should flow in this direction. Now I can replace like this, right? So for this current, whatever the current which is induced in the coil should oppose. Should oppose, right? So positive, negative if I consider, it will oppose, right? So this is 2 amperes. And what will be the EMF? So we can calculate or not? E equals to L di by dt. So what is L? 2 millihenry 10 to the power minus 3, and di by dt is 1 ampere per second. So I can write it as 2 into 10 to the power minus 3 again. So this is the induced EMF, right? So what is the EMF of this battery? It is 2 millivolt. 2 millivolt, right? So now remaining terms will be same. This is 5 volts and this is 2 ohms and this point is B and this point is A. So we replaced. Now we can apply the current electricity concept. What is that? We have to start from the point A, or we can start from there also. Okay. So I am starting at point A. First what we got? Positive terminal. So negative. So negative 2 millivolt. Again positive terminal, so minus 5 volts. In the direction of the current we are traversing. In the direction of the current. So what will happen to the potential here? Decreasing. So decreasing potential, minus again. So what is that? 2 2's 4. V equals to IR. So I is 2 and R is 2. So 2 2's 4, which is equals to VB. Okay. If you didn't understand this, please revise current electricity concepts and come back, you can understand. Alright. So VA minus 2 millivolts, minus 5 volts, minus 4, which is equals to VB. Now what I can write? So this is also in volts only, right? So VA minus VB I asked to calculate. So everything is in minus, so it then go that side. So it is 2 into 10 to the power minus 3. So how I can write this one? 0.2 10 to the power minus 2, right? So it is 0.002, can I write? Minus 1, minus 2, minus 3, right? So plus 5 volts and plus 4 volts. So finally VA minus VB which is equals to, it is 9.002 volts. So this is the potential difference between A and B. Right? So positive terminal, negative, positive. I said in KVL and KCL rules. Please go through there and try to revise. Minus, minus in the direction of the current, again minus. So which is equals to potential at this point. So we have to add everything. So this will be the potential difference. Now decreasing in the sense, this battery terminals will change. That you have to think. Remaining things will be same. Right? So with this self-induction concept is completed. We will continue in the next class. Thank you.